Hello, my name is Greys Sosic, and I am a professor of operations and supply chain management in the Data Sciences and Operations Department at the Marshall School of Business. In my latest paper, I am exploring whether we can do desalination better by reducing the amount of concentrate that requires disposal and the amount of salt imports in the US. Water scarcity has been a global problem for some time, and the climate change is making it worse. Water stress, or the ratio between the demand for water and the available amount of water, is globally at 11%, but there are over 30 countries in which it exceeds 25%. What these numbers hide are the regional differences within a country. For instance, while the US has a water stress level of about 22%, several states like California or Arizona exhibit water stress of 40% or higher. As the world population continues to grow and temperatures rise, water availability is becoming ever more critical, and conventional water supplies that rely on easily accessible groundwater, rainfall, and snowfall are not sufficient to meet population needs. Several unconventional water sources, such as fog water harvesting, cloud seeding, water treatment and reuse, iceberg towing, and desalination, which will be our focus, are receiving more attention in recent years. In 2019, cumulative installed desalination capacity worldwide exceeded 28 billion gallons per day. Two of the biggest feedwater categories worldwide are seawater at 61% and brackish water at 21%. On average, salinities in the open ocean have ranged from about 34 to 37 parts per thousand, while brackish water can be defined as water containing between 1 and 15 parts per thousand. In the US, 97% of desalination plants use brackish water, and only 3% of facilities treat seawater. While the most likely reason for this is higher cost of seawater desalination due to its higher salinity, at the same time, we should also note that seawater represents a freshwater source of almost unlimited capacity, unlike brackish water. Technological advances in recent years have led to a significant cost reduction in water produced by desalination, making this option more attractive. At the same time, more stringent regulatory requirements led to the increase in cost of conventional water treatment and reuse. Climate change impacts the availability of water supplies and may require water providers to pump groundwater from greater depths or move it over longer distances. As a result, the United Nations estimate that desalination is likely to be the most acceptable alternative water supply source in the majority of arid and semi-arid regions in the world. The growth in desalination has highlighted the need for cost-effective and environmentally acceptable techniques for freshwater extraction and residual concentrate management. Most coastal desalination facilities discharge residual concentrate to the ocean, while inland locations use surface water discharge, deep well injections, or zero liquid discharge technologies. All of these methods have potentially negative environmental impacts, and action needed to reduce this impact could be quite costly, with costs ranging between $24,000 to almost $4,000 per metric cubic per day. At the same time, more than 290 million tons of salt are produced worldwide annually. In the US, production in 2019 was about 42 million tons, and over 16 million tons were imported. The biggest sources of imported salt were Chile, Canada, and Mexico. For salt consumption, the biggest categories are highway de-icing at 43% and chemical industry at 37%, with food processing using only 4% of salt consumed. Salt production costs can vary significantly. Soil salt production uses seawater in evaporation ponds, which then leaves behind salt. While this methodology requires large land areas for evaporation ponds, its energy requirements are low and reflected in the production cost of only $5 to $10 per ton of salt. Vacuum salt production is the costliest, as it requires higher equipment and energy costs, with production costs of $30 to $50 per ton of salt. These costs work if the salt is consumed close to the production site. To obtain actual consumer costs, these values have to be augmented by transportation costs, which can go from about 3 cents per ton mile by water up to almost 19 cents per ton mile by truck. What we do in this paper is first, we analyze existing desalination operations in the US. Next, we analyze current supply chains for importation of salt to the US. As previously mentioned, transportation costs can be a significant factor in the total cost of purchased salt, and locations that are further away from salt sources face higher salt prices. In this study, we focus on imported salt that must be transported over longer distances and thus implies higher costs, making it a potential candidate for replacement with co-produced salt. Lastly, we look at the 3 states that currently host most of the US desalination facilities, California, Florida, and Texas, and we compare the energy requirements, costs, and greenhouse gas emissions for the status quo and for the salt freshwater co-production. We first discuss current water desalination operations in the US. As of 2017, there were over 400 municipal desalination plants in the US size 95 meter cubics per day or greater, with 167 facilities located in Florida, 58 in California, and 52 in Texas. The average US desalination plant size tends to be rather small, although there are a few exceptions, most notably plants in Carlsbad, California, which processes seawater, and San Antonio, Texas, which processes brackish water. The sizing is important because larger plants tend to achieve economies of scale, resulting in lower cost. These cost differences are illustrated in this table, where we can see that desalination of seawater requires more energy due to its higher salt content, and the prices per meter cubic tend to decrease with the plant capacity. In 2019, the US states imported over 16 million tons of salt. Here we present total imported quantities and values for the top 12 US salt importers in 2019, responsible for almost 80% of imported salt. All the top US salt importers are located rather far from California, one potential location for co-production plants. As shipping costs from California to most of these states might be too high to make co-produced salt competitive with salt imports, we also investigated imports to Western US states, which might be better candidates for receiving their salt from California. Unfortunately, the amount of salt imported to these states is rather low, and California and Washington are the only states in the group that import a somewhat significant amount of salt. So we added them to our analysis. As mentioned earlier, biggest sources of imported salt are Chile, Mexico, and Canada. To this group, we also add the Bahamas, as it is a large source of Florida salt. Thus, in this map, squares represent potential plant locations, ovals represent the origins of salt imports, and the shaded areas are salt import locations. For the production of salt and fresh water, we used the model developed by Nayar and his co-authors. They assumed that the seawater feed with salinity of 35 parts per thousand first flows into a reverse osmosis system, where freshwater and desalination brine are produced. The brine, with a 60 parts per thousand salinity, is then concentrated via an electrodialysis system to a salinity of 200 parts per thousand. The concentrate is sent to the crystallizer, where it is separated to pure salt, water, and purge. Co-production could lead to significant reductions in requirements for concentrate disposal. While reverse osmosis seawater desalination requires proper disposal of about 58% of the intake volume in the form of concentrate, co-production requires disposal of only about 1.7% of the intake volume, or about 35 times less. In our model, we assume that no importing location will be willing to pay more for salt than what they are currently paying. We analyze the case in which we assume a federal level decision maker is choosing locations for co-production facilities and finds optimal configurations for different numbers of plants under consideration, ranging from a single plant to 8 possible plants. Our analysis indicates that maximum number of plants that are feasible in this case is 6. If we want to sell all co-produced salt with more than 6 plants, we have negative revenue for some plant market pairs. California is never chosen as a co-production plant location, as it is located further from demand points in the remaining 2 states, thus leading to less competitive shipping rates. Building one facility in Texas, or one in Florida and one in Texas, leads to the water cost below the current average desalination cost. However, once we build more plants, the net co-produced water cost exceeds the current desalination cost. As the ocean has an almost unlimited capacity for desalination, these options might become attractive as water becomes even scarcer and water prices increase, while at the same time co-production costs might decrease due to technology advancements and implementation of a carbon tax. Almost all of the configurations lead to some level of greenhouse gas emissions reduction. As a result, introduction of a federal carbon penalty legislation can lead to a further decrease in net water prices. However, once we build 3 or more plants, a very high carbon tax would be required to induce cost parity. In our analysis, the total demand for imported salt considered is about 1/2 of current US imports. Extending the analysis by considering total imports may indicate that even more co-production plants might be currently feasible. One important element not included in our analysis is the change in required inventory levels if imported salt is replaced by co-produced salt. While demand for many salt types can be rather stable, this is usually not the case for road salt. For this reason, many states have quantity flexibility contracts with their salt suppliers that require the suppliers to keep extra inventory. At the same time, the states have the option to not purchase the entire contracted quantity. As an example, salt users in New York State are obligated to take at least 70% of their order quantity, while contractors are obligated to deliver up to 150% of the order within a specified time window. Our analysis of ocean shipments from Chile and Mexico to the US East Coast indicates that the ocean portion of the trip takes between 17 and 21 days. Thus, suppliers in states that rely heavily on imported salt from Mexico and Chile may need to keep high inventory levels due to long lead times. When considering rail shipments of co-produced salt from Houston, the travel time varies between 3 and 18 days with an average of 10 days. Similarly, the travel time from Miami varies from 6 to 12 days with the average time of 10 days again. Hence, the use of co-produced salt can lead to lower inventory levels, on average between 30 and 40%. Recall that we mentioned that 43% of the US salt is used for de-icing. Thus, this inventory reduction can further reduce the cost of co-production option and make it more attractive. In summary, our analysis indicates that building a small number of strategically located co-production plants in the US that would sell co-produced salt to states that are currently importing salt would result in a decrease of the net cost of desalinated fresh water. The results become even more positive if we account for potential reduction in inventory levels of road salt and if a federal carbon tax is implemented, in which case building more plants could be both feasible and financially more attractive. This fact is even more important when we take into account freshwater scarcity and seawater abundance. We hope that our findings are useful for government and corporate decision makers when considering the type and the location of desalination facilities to build, as well as the environmental policies that are implemented. For instance, while building co-production facilities in California is not financially justified at the moment, it would be environmentally beneficial as it leads to reduction in greenhouse gas emissions. Moreover, it might be financially attractive in the near future due to increased water scarcity in the region. On the other hand, due to its central location, Texas is the state that achieves the lowest net water cost from co-production, but building such facilities in Texas increases greenhouse gas emission and has negative environmental impact. At this point in time, locating co-production plants in both Texas and Florida leads to both environmental and financial benefits. Thank you.